All right, this is going to be a little bit lengthier video. I'm not sure I like that or not, but this is one of the 2 times during the year I really do give notes on things, and I really need you to try to pay attention, doing a couple spots, breaks, stuff like that. Maybe that'll help out. At any rate, this is also one of the more formula-ish parts of the year, and so I'm going to give you a new formula sheet. Looks just like the old one on the front. It has some of the formulas from first semester on the back. We're going to have new ones. I put those on the back as well. Remember, you can write other things and use these on any tests or quizzes, but you should keep it updated. You can use either the one from first semester or the one from second semester, not both. So pick one if you want to use it. I'll give these out in class. So I want to just refresh your memory that, first of all, if you have extra questions, the physics classroom tutorial on 1D kinematics lessons 3 through 6 is a place you can go. So you can decide whether you go there or not, but it's very helpful. The other thing is I want you to remember that this triangle symbol means change in or difference in. So that's the Greek symbol delta. So sometimes you hear people talking about, well, there's a big delta in that. It just means there's a big change. Yeah, you'll hear it from time to time. We typically measure displacement or distance in meters and speed or velocity in meters per second. And in science world, we measure acceleration in meters per second per second. So with this, we already know some of these things from things we've done with our graphs. So for example, if we take a position time graph and we look at the slope of that, that's the change in position over a time interval. So the slope of a position time graph tells us velocity. This isn't anything new. So this formula is going to be something we use a lot, and it's something we want to actually kind of quantify. Same way, acceleration is the rate of change of velocity with respect to time, so change in velocity over change in time. So it's the slope of a velocity time graph. So that's something we've done also. Here's an example. So the sample problem is, let's say you're driving along your car, really slow in a speed zone at 10 miles per hour, and you get to the end of the speed zone, and you floor the accelerator, you go from 10 miles an hour to 70 miles an hour in 10 seconds. That's a known rate of acceleration. Well, we're increasing our speed by 60 miles per hour in 10 seconds, or 6 miles per hour per second. So that's a rate of change of speed of 6 miles per hour for every 1 second. That's what an acceleration is. Now, we just happen to use units of meters per second. Sometimes, and a lot of times, they're abbreviated as meters per second squared. That's kind of can be confusing. It's not that the units time is squared, it's that we're squaring the quantity. Or pardon me, let me fix that. It's that the units here are squared. So it's meters per second. That's why the units have a square symbol at the bottom. Sorry about that. So we've talked about already objects at rest. We know what those are. They're quite simple. We've also already discussed objects that are moving at a constant speed or constant velocity. For example, your buggy lab and those constant velocity sheets. And we've also already talked a little bit about objects at changing speeds that can have a positive or negative acceleration. We will not have changing accelerations. We will always have a constant acceleration because we're not in calculus class where that makes more sense. We've also already used Newton's second law to figure out acceleration if we know forces and masses. So for example, A equals F net over m tot, or total mass, something like that. And we can measure that in newtons per kilogram or meters per second squared. On the surface of the Earth, the gravitational acceleration is known as little g, and that acceleration is 9.8 meters per second squared, or newtons per kilogram. We found that out in a gravitational force law lab. You could also use 10 meters per second squared if you so choose. So that's fine as well. In the absence of air resistance, objects all accelerate at this rate, and that's called free fall, which just means that gravity is the only force acting on the objects. So the reason we end up having the same acceleration for all objects on Earth is that if you think about it, the gravitational acceleration is just a ratio of net force to mass. So if I have something It's got a certain mass, say 1 kilogram. I've put something on top of it that's 2 kilograms. Well, this has 10 newtons of gravitational force acting on it. This would have 20 newtons of gravitational force acting on it. The ratio, whether it's 10 over 1 or 20 over 2, stays the same. So close to the surface of the Earth, that gravitational acceleration will stay the same. So as we get into these motion formulas, and there's going to be a total of five of them, we end up seeing that they're vector formulas. So the direction matters. So we can have positive and negative velocities, positive and negative displacement, positive and negative acceleration. So once again, you can go to the physics classroom tutorial, chapter 1D kinematics, lesson 6, which goes through a lot about these things. You don't necessarily need to memorize those, but you should have them on your formula sheet. So the physics classroom does use the symbol D for displacement, but most physics texts use the symbol X or S. All tend to use X most of the time. So don't be confused about that. All right, here we go. We've got three formulas right off the bat. This is one you already know. So speed or velocity, speed is distance over time. Velocity is displacement over time. Which is a change in position over a time interval. So we've got delta x over delta t. Now, we can rearrange that a couple different ways also. So for example, if we wanted to solve for time, we could say delta t, or time interval, is delta x over, this, by the way, is average velocity, over average velocity. Or we could say my average, if I want to find my displacement, delta x, that's equal to average velocity times time interval. And again, sometimes you see things that use the delta and sometimes you don't. We're almost always talking about an interval. So that's actually right over here. If we have an object that's moving at a constant velocity of, say, 5 meters per second, and it's doing that for 10 seconds, we know we can use the area of a velocity versus time graph to figure out displacement. So in this case, I get 5 meters per second times 10 seconds. That says that this thing has a displacement or moves 50 meters in that time. So the area of this rectangle is V average times time. That is a version of this formula. Another version, or another way to find average velocity, which we really don't tend to use very often, but it is useful occasionally, is this one, which says we have an average velocity, and that's equal to the final velocity plus the initial velocity divided by 2. And what I really need to do here with this is I need to put this down as having parentheses around it. Because if you just enter it like this in your calculator, you're going to end up goofed up. So let's say, for example, I have an object that starts at 2 meters per second and ends at 12 meters per second. And I want to find the average velocity. It should be halfway between those, right? So that kind of makes sense. So I would have 12 meters per second as my final, plus 2 meters per second as my initial, divided by 2. But if you don't put this in parentheses, that is a weird 2. Your calculator is going to do 12 plus 2 divided by 2. Well, 2 divided by 2 is 1. 12 plus 1 is 13. You can't have an average velocity of 13 meters per second when the fastest you ever move is 12. And so you always want to be making sense when you're doing calculations, not just plug and chug in your calculator. So if I put a parentheses around that, what I'm getting is 12 plus 2, that's 14. 14 divided by 2 would be 7 meters per second. Sure enough, that's halfway between these things, between 12 and 2. So that's our second formula. Our third formula is one where we're looking at acceleration. So acceleration, we said before on the front page, is change in velocity over change in time. This version of it says final velocity minus initial velocity over change in time. Really, that means the same thing. So in this particular case, it's not there. This acceleration, delta v over delta t. You can also do things, say, time interval. You could rearrange this algebraically. Is delta v over acceleration. That can be very useful if you want to find the time that an object's been accelerating and you just know the difference in velocities. So that can be useful. So that's a rearrangement. Other rearrangements are over here. And again, these are just algebraic. Our final velocity is equal to our initial velocity plus acceleration times time. What does that mean? Well, let's say that we have an initial velocity of 5 meters per second, and we're accelerating at 2 meters per second squared for 3 seconds. At 0 seconds, I'm moving 5 meters per second. After 1 second, I've added an additional 2 meters per second. So 5 plus 2 would be 7 meters per second. So I'm adding 2 meters per second every second. I'm doing that for 3 seconds. So 5 plus 2 times 3, I mean after 3 seconds, my final velocity would equal 11 meters per second. The same way, we have something here. If I want to find my initial velocity, it's my final velocity minus acceleration times time. So you may want to write all 3 of these versions down, but it really is just algebraic versions of the same formula. All right, the fourth formula is down here, and it's actually the toughest one, I think. So if you remember up here, when we looked at this, we said the area of this graph is 5 times 10, 50 meters. This formula, number 4, is essentially going through, and there's several different versions of it. It is plugging this second formula and a version of this first formula together, and it's coming up with a formula for the displacement of accelerated objects. Essentially, if you accelerate from rest, you'll be looking at this 1/2 at squared, 8 times t times t. If you accelerate from something where you're not at rest, it's the initial velocity times time plus 1/2 acceleration times time interval squared. I don't think we're going to use this last one at all. So the idea behind that is if we get an average velocity and the initial velocity starts at 0, then we could say that to find our displacement, our final velocity divided by 2 is equal to time. But up here, we said our final velocity is equal to acceleration times time. If we start from rest being 0, so acceleration times time divided by 2 times time. It's kind of a mess, right? So there's another way to think about it. So I want to do this example down here. I'm just going to contrast with this example we did earlier. So keep in the back of your mind that the earlier example we had an area of 50 meters. So down here, if I look at this, I'm starting at 0, and from up to 10 seconds, I'm accelerating up to 5 meters per second. So if I want to get the slope of this graph, it would tell me the acceleration. That's using formula 3. So that's 5 divided by 10. So the acceleration in this case is 0.5 meters per second. So I'm going to write that up here. So 0.5 meters per second That's the numerical value. We're going to come back to that in a minute. Now, I've also talked quite a bit this year about how to take a general equation and make an equation for your specific graph. So if we think about our general version of equation, which is y equals mx plus b, here our y-axis variable is velocity. It's really a final velocity after a certain amount of time, but I'll just put v. Our slope is acceleration. So that's acceleration. And our x-axis variable is time. Notice that's, again, back a version of formula number 3 up there. And in this case, we're starting from rest, so we have no y-intercept. So we could think of the velocity as being the same thing as acceleration times time. So over here, I could say this axis is velocity, where I could say it's acceleration times time. Well, we already know that the area of a velocity time graph gives us displacement. So in order to get the displacement of this, I'm going to get the area of a triangle. So the area, 1/2, you could say base times height or height times base. I'm going to say height times base. In this case, that area, 1/2. I could say velocity, but I could also say acceleration times time. And on this axis, it's time. So I get the area is equal to 1/2 acceleration times time times time. And that is 1/2 AT squared. That is this fundamental version of this formula. So whether you want to go through all that proof or not, the idea is that these formulas aren't just magic. They don't come from nowhere. They basically come from what we already know and the fact that the area of this graph is the displacement. So let's go through and actually do this now with this graph's values. The area of this is equal to 1/2 height, which is 5 meters per second, times base, which is 10 seconds. That's 25 meters. If I wanted to use the formula 1/2 AT squared, I could say 1/2, said the acceleration was also 1/2. The time is 10 seconds. We square that quantity. 10 squared is 100, times 1/2 is 50, times 1/2 again is 25. Same answer, 25 meters. Now the other thing is, if you remember, when we had our graph before with a constant velocity of 5 meters per second, it had a displacement of 50 meters in the first 10 seconds. This is half as much. Should make sense because we're starting at 0, we're ending at 5 meters per second. Okay, a lot of math. A little bit more of an explanation there. I will end up putting these notes up as part of this assignment. You can choose to look at them or not. If you want a hard copy, let me know. So now I want to do another example. This is just to get a white background. So when I take a look at this, I want to do an example where we don't start from rest. Okay. So I want to do that in this white area right here. So let's say I've got a graph and it's a velocity time graph measured in meters per second. And let's say I've got a constant velocity here initially of, say, 3 meters per second. That's going to be 2, 4, 6, 8, 10. These are times and seconds. So 3 meters per second there. And let's say we're going constant velocity during the first 4 seconds. And then, let's say we're going to accelerate to a value of 12 meters per second at the end of this time interval. So we're going to end up somewhere like that. Well, I could get this answer graphically. I could figure this out. And the way that I could do that would be to split this up. I've got a rectangle here. I could use a constant velocity formula. I'm going 3 meters per second, and I'm doing that for 4 seconds. 3 meters per second times 4 seconds would be 12 meters. That's this area of that rectangle. What about this from 4 to 10 seconds? Well, if you look, it looks like a trapezoid. If If you remember the area of a trapezoid or how to get that, you could do that also. Or, because I'm not very good about remembering that, I can split it up into another rectangle and a triangle. Okay, so that'll work. And it also relates back to the formulas. So if I think back to the formula for calculating things, with a constant velocity, it's velocity times time. So that's what I did here. So I had 3 meters per second and a 4-second interval. That was 12 meters. That's the displacement during the first 4 seconds. What about during the last 6 seconds? Well, during the last 6 seconds, again, I'm accelerating. And I can think about, I would do something like this. VI times t plus 1/2 a t squared. So I could do that as the mathematic version. Well, how do I do this in terms of this version? I could get, again, the graphical version, the area of those two things. So if I want to handle this graphically, I could simply do the area, base, or height times base. So that's 3 meters per second, multiplied by this interval, which is from 4 to 10 seconds. So that's 10 minus 4, or 6 seconds. 1/2. The height here, 12 minus 3 is 9. And the time is, again, 6 seconds. So this would come out to 3 times 6 is 18 meters, plus 1/2 times 9 times 6, 54 times 1/2, that's 27 meters. So that would equal 45 meters during this time interval from 4 to 10 seconds. Well, how can I get that mathematically using a formula? I need to be able to get this acceleration. The acceleration is simply the slope of a line. So this slope I can find by saying change in velocity over change in time. (12 minus 3 is 9 meters per second, over 10 minus 4 is 6 seconds. The acceleration is 1.5 meters per second squared. So now I can go down here. So this displacement, my initial velocity, still 3 meters per second. The time interval is from 4 to 10 seconds now. So I'll say 10 minus 4, or 6 seconds, plus 1/2. Acceleration I just found is 1.5 meters per second squared. The time interval, again, 10 minus 4 seconds, or 6 seconds. Right? Let's go ahead and do this. 3 times 10 minus 4 is 6, plus 10 minus 4 is 6, 6 squared is 36, 36 times 1/2 is 18, 18 times 1.5 would be 27. So I end up getting 18 plus 27, those 45 meters. Same way as looking at the graph. So the total displacement during all 10 seconds, I have to take this as kind of like a piecewise function. I don't know if that's what they call it or not. But I have to look at the fact that I had 12 meters here and 45 meters in all this. So that would end up being a total of 57 meters. Okay? Pretty detailed example. All right. There's one last formula, and I'm not going to spend the time deriving it that I have for these other ones, because you don't want me to do that. But it will be in the notes. That is not good erasing. So that formula is down here. And basically this derivation is combining two of the other earlier formulas. And essentially it is v final squared is equal to v initial squared plus 2a times delta x, or displacement. So oftentimes we do this when we think about an object where the initial or final velocity is 0. And one of the reasons this particular equation, number 5, is so useful, and by the way, this is the version where essentially to get this all by itself, you'd have to take the square root of everything on the right over here. But the reason it's so useful is, if you notice, it doesn't involve time. The reason that's true is we're setting two equations equal to each other, and we've rearranged each of those for time intervals. So basically we're setting the right side of this equation equal to the right side of this equation. That's how we come up with that. So with that being said, the next part of this is going to end up being a second video. It's going to be not quite as long, and I'm going to go through several other sample problems. On the back of these notes, by the way, there's some nice graphs relating velocity, acceleration, change in velocity, things like that, and what it looks like on a graph. And there's a sort of a Cliff's Notes version of it down here. All right, thanks. That was a long one. Have a great day.